So hi everyone and welcome back to the channel and welcome to 2024. Now it's not often that something lands on my desk, particularly from the bike engineering side of things, where I go, that's really clever. Free up sound check for you. And then this landed on my desk about 3 or 4 months ago, and I've been riding this system on my mountain bikes since I got it, and I am fully converted. Back to school today, we're going to do a redesign and a complete relearn of the legacy rear hub and the free hub system, and why I think this kind of system should be adopted for all bikes going forward, because it's pretty much superior in every way. And it's fully patented, so you can't copy it, but it's super clever how this works. And if an alien with a PhD in engineering, and he landed on Earth, or she, or it landed on Earth, I think aliens are non-binary, and you said, design me a system that can go on a mountain bike or a road bike, has heavy loads going into it, all different load directions, chain forces, bump inputs, rider weight, can freewheel, so I can stop pedaling, and the bearing life has to be amazing. They might come up with something like this, having not looked at the legacy hubs which we've been dealing with for about 30 years. So don't forget that the free hubs and rear hubs design that we've been dealing with for about 30 years hasn't changed. Product design and product development, let's say, for kind of mass volume production, it's not always the best solution that's chosen by the engineering manager. How this might go, so you might have 5 or 6 design engineers in a room, well, probably only 2 or 3, asked to design a number of different ways to produce a bicycle free hub. Each engineer might propose 3 or 4 different designs, and they all get rated based on the engineering functions, so high stiffness, low weight, bearing life, bearing loads, but also in terms of cost of production, how small is the bill of materials, how much is the inventory going to cost, what are the logistics like, how nice it can look, and it's all those consumery type things which end up devaluing the engineering function part. So the engineer will never really get his best engineering function design chosen by the manager. Now, if you work in defence or, well, actually maybe not, that's such a good one, but motorsport or anything really R&D based like NASA, then it's kind of not so important about the low cost and, you know, the bill of materials and things like that, and you can really push the engineering function parameters up. But what I'm trying to say is I don't believe the current rear free hub design is optimum really in terms of the engineering function at all. I think it'd be a lot better, and this is where this comes in. This doesn't really have the drawbacks like those other things of high cost, bad inventory, high bill of materials. It's actually very, very simple. So this is why I think this is a real game changer. And quick free hub sound check for all the tarts out there. Did you notice that? The free hubs on the disc side? Yeah, weird, isn't it? We're going to go back to school, we're going to rethink it, relearn it, and let's see if we can redesign this hub. Now, this hub was sent to me by a company called KOM. They're based in the UK. It's the brainchild of an aerospace engineer, and they came to the Peak Talk channel for its marketing prowess. Crazy, isn't it? But here we are. I've been riding it. I've been thrashing it on my new Mega Tower, which is taking some knocks already, and I can't fault it. So let's have a quick recap on how legacy hubs work. They're not great, but they work. For most people, they work absolutely fine. But when you push the limits on mountain bikes and e-bikes, they tend to break down pretty quickly. So I've hopped into the CAD. I'm going to describe the load path briefly again. Now, I did something similar to this in a video about 3 years ago, describing the load path and how bearings and axles work in free hubs and how preload system works. So I'll leave links to those videos down below. This is how I'd say most hubs have been done for the last 40 years, apart from Shimano hubs, which use loose cup and comb bearings. But cartridge hubs bearings or sealed bearings, this is how they're done. So you basically got 4 bearings on a shaft. The shaft in road bikes now or mountain bikes is 15 millimeters, or it can be 17 millimeters on the rear. But essentially, you got 4 small bearings on a shaft. Now, the free hub bearings on the right-hand side of the screen here, they are kind of floating on the shaft. So that's obviously pushed on because you can pull that off quite easily. And the free hub body itself, this part in orange, isn't fixedly connected to the rest of the hub. So it's really not taking a lot of radial load from the rider weight or bump inputs. It's kind of just floating around, but it does deal with the chain forces and the applied torque. Essentially, well, it can't react torque, but it takes the chain force and transfers it to the ratchet. So essentially, you've got your rider weight coming in on these 2 spoke flanges, obviously through the tyre, through the rim, through the spokes, and then up into the hub body here. Now, that load path basically is shared between these 2 main bearings in the hub body. The problem with this is this main hub bearing here is very far away from where the axle is supported. Essentially, the axle is supported at the ends, at the dropout. That's where it's fixed. But your load is coming in mainly in this main hub bearing in the middle. And that, in terms of engineering design, is an absolute sin. You would never design a shaft like that with bearings in that position because the bending moment is huge. So if you fixed your shaft at the end and you've got most of your bearing load coming in somewhere in the middle, you're going to get a lot of flex in the shaft. And because this shaft is so small, the shaft will actually bend. And I'll drop in some FEAs. Obviously, these plots are massively amplified, the displacement, but you get a lot of localized bending in that shaft because it's supported right at the end and the load's coming in at the middle. Now, we'll see how this absolutely nails this problem in a minute because it's got basically bearings right at the edge and the free hub goes from here all the way to the other side, which is super clever. And why is a bendy axle bad? Well, it obviously gives you lack of wheel stiffness when you grab the tyre at the top and you can feel it bending. Some of that is coming from the axle bending. Obviously, it's coming from the bearing clearances as well if they're not taken out very well by preload, and it comes from the spokes and the rim, whatever. But the main pivot of all that flexure is right in the middle of the wheel, down at the hub. Now, some people say flex is a good thing in a wheel, but it's not good for the axle because it really damages the surface of the axle. And I'll drop in pictures here of damaged axles that have been locally deformed underneath the hard steel inner races of bearings where they fretted and you know, that micro bending has fretted away the aluminium. That'll then cause the bearing to spin sometimes and cause further damage on the axle. But the biggest problem with a bendy axle is what it does to the bearing life. So any slight misalignment between bearings is terrible for bearing life. So really you want a very stiff layout where your bearing life can be maximized by having no misalignment between the bearings. And it's exactly the same in a bottom bracket, of course. You've got to think, so the main structural component of the rear hub which bends is this red axle. And normally this is 15 millimeters or 17 millimeters. Now, when you increase a size of a tube, so if you increase the diameter of a tube without changing the wall thickness, the stiffness goes up by the power of 4. So the bending stiffness of a cylinder goes up by the power of 4. Let me just repeat that. It's crazy how much stiffer a tube gets if you just grow it a little bit. And that's why I did in another video, like carbon fiber frames versus aluminium frames. If they're the same tube dimensions, basically, they're not actually any stiffer. Because once you do the layup of carbon, it remains at about 70 gigapascals with a cross-ply layup. And it's really the diameter of the tube which gives anything its stiffness. And for instance, the tube in this, well, it varies sizes as it goes throughout the hub, but I think the nominal size is about 32 mil, which is 20 times stiffer than a 15 mil tube. It's actually got two axles. There's an axle, a center axle, which is 90 mil, and then the free hub axle goes all the way through, and that's 32 mil. So I'll come to the bearing layout in this now, but first of all, we have to go back to school and look at that legacy free hub. The thing you need to maintain from this, or take away from this, is that you need near perfect bearing alignment to maximize performance of the bearings and keep their bearing life as it should be. This is the cross section of this. I'm going to put this down now, so concentrate on the screen. I've highlighted the bearings in red, so you've got 4 main bearings in red. Now, unlike the free hub of the legacy hub design, that can't really react any rider weight, whereas the bearings in this, all 4 essentially are in the load path. So let's do the load path check again. The rider weight is coming in through the hub flanges, obviously from the tyre, rim, spokes, up into the hub flanges. It's up into these main big bearings here, the first 2 red bearings here. That load is then transferred into the free hub shaft, what I'm calling the free hub shaft, which is the large orange part. And that load is fixedly connected to the free hub bearings. And the free hub bearings are right at the edges. So you've got a red one here on the right-hand side and another massive one here on the left-hand side. And that passes the load into the blue axle, which is the 19 millimeter center axle, into the end caps and into the frame. So all of these bearings are in the load path. And the beauty of this is the first 2 bearings in the outer hub shell, they pass the load to the bearings right at the ends of the inner axle. So these 2 bearings here on the far right and the far left are very, very, very close to the dropout. So the bending moment on this axle is essentially as close to 0 as it physically can be. It's as close to a pure shear force diagram as you can get, and the bending moment is very, very small. Now, I'm not going to bore you with kind of engineering mechanics year 1, but if you want to learn more about bending moments and constraints and shear forces, you can look that up. But this is beautiful in how this works in taking the load path, which is essentially from the middle of the hub, transferring it to as wide as it can be. And before we go on, that's the same as cranksets. This is why I hate BB30. When BB30 came out, you got 2 bearings, which are like on the inside of the bearings about 50 mil apart, and then your Q factor, where the load is going on, could be 160. So your load application is very, very far away from where the bearings are supported, and that's why you got so much fretting and damage and flex on those BB30 axles. It just was a crap layout. In general, you want your bearings as wide as possible to the supports so the bending moment is lower. Now that's a bit different to a hub, but it's kind of reversed. But yeah, bending moment as low as you possibly can get is ideal. The other thing you might notice is the free hub ratchet and pulls all the way over on the other side underneath the disc brake, and that has its own benefits. And KOM actually making their own disc brakes for all different sizes. They're 4-bolt. You lose the center portion of the disc brake, so the disc is actually slightly lighter. And the beauty of this ratchet is the ratchet ring, as you can see here in the end, and the pulls are about twice as big as they would be if they're tucked away in this end in like a legacy hub. And that comes for other benefits, as we'll see in a minute. But going back to the bearing layout, very, very big bearings, all in the load path, and the outer free hub shaft runs all the way through the center of the hub, which makes the free hub really, really stiff. So when you've got your cassette on the free hub and the chain force is pulling it that way on a normal free hub, because it's basically floating on the axle, it can twist and it will skew. It's not a uniform loading on those two bearings. So microscopically, it can actually skew the free hub, and you get quite a lot of digging in on the bearings on the axle, and it can damage the axle. Now, for lightweight road riders, that might not be a problem, but if you're punting out 1,000 watts regularly or 300 Newton meters on an e-bike, that is really, really problematic for those two little free hub bearings to deal with, which is why this full-length free hub, supported at both ends, is so much stiffer, because it's much harder to skew that whole free hub. Now, the other thing about this is the bearings are arranged in pairs. You've got a pedaling pair and a free hub pair. When you are pedaling, it's only this bearing and this bearing that are spinning, because these are stationary, because the whole thing's moving together. Then when you start to freewheel, this bearing here, this large bearing and this large bearing start to spin, and these become stationary. So at any one time, you've only got two bearings spinning, which makes the pedaling drag lower and the free hub drag lower. Now, of course, these bearings are slightly bigger, so naturally they're going to have a higher kind of friction rating anyway, but that needs to be tested. But essentially, you've only got two bearings moving at once. Now, the low drag side of it, the efficiency, that actually hasn't really been tested, because we're talking so small efficiency gains here. It's very, very hard to test that. Now, talking about efficiency, this brings me back to the classified efficiency test, where they compared their hub in this kind of locked out ratio versus a DT240 on a torque test machine. Now, when I discussed that, I said a limitation of this test was that there was no rider weight applied, no radial load applied to the hub. When you load that hub in the middle, you do get a significant bending on the axle, and that's going to massively increase bearing drag. So when classified or DT Swiss say their hubs are 99.8% efficient, they really need to be doing that test with rider weight simulated, like a static load pushing down on the axle, because that bending will increase the bearing drag. That problem is somewhat mitigated with this hub design, but I don't think KOM have done the testing, like their test rig is in the works to try and prove some small efficiency gains. But that's not really the main selling point of this. The main selling point is the strength and durability. I'm talking about that bending stiffness quickly. Here's the results of the Sheffield Hallam deflection testing. So this is their test rig. They've basically done a 2-point bend test with, well, kind of a 2-point bend test, but they've applied the load to each hub flange with this flexural pivot here in an Instron machine, which is a tensile test or tensile compression machine, the best in the industry. And they've measured the deflection. As you can see here, the ultimate deflection of the KOM hub is much, much smaller than the DT Swiss or the Hopes. And then as you deflect that middle hub bearing downwards, you actually get a relative angular displacement of the hub shell, and you can see how stiff the KOM is in comparison to the DT Swiss E13 and the Hope hubs. So that's why, when you grab the tyre at the top and you move it in the bike, it feels exceptionally stiff because of the stiff axle and the way the bearings are laid out. Now, I hope you're still with me, because I appreciate this is very, very geeky, but we have to kind of go back to first principles of hub design to get through this stuff. And I want to talk about something that isn't really spoken about enough, and it's a problem in all hubs that have outward flinging pulls and ratchets. Not so much of a problem with the star ratchet system from DT Swiss, which more hubs are taking on. But it's something called single pull engagement, and it's a load case which is basically the killer for all hubs. It kills the bearings and it kills the axles. Industry 9. If you look at Industry 9, most of the stuff on their website is replacement axles because of this problem. Now, single pull engagement is a load case where momentarily only one pull engages with the ratchet ring, and that's just due to manufacturing tolerances, to small clearances, to small bearing tolerances and deflections. At one time, when you first load up that ratchet with pedaling, it's likely, or it can happen, that only one pull is engaging right at the start. Now, the reaction load of that only engaging on one tooth bends the axle with an equal and opposite force to your pedaling load very, very quickly until the other pulls kind of take up the slack and then they're all engaged. So I'm going to run downstairs, get a little free hub. I'm going to show you what I mean. Now, like it or not, this happens in pretty much every hub with an outward flinging pull system, but you just don't notice it. But it is damaging to axles. Now, what you hope happens when you... My fingers here are going to simulate the ratchet ring, okay, the toothed ring. When you apply a load to the free hub, you hope that all those pulls are engaging equally, instantly. But actually what happens is when you apply a torque, more often than not, only one pull engages. And what does that do? Well, it shunts the whole free hub downwards or radially in a direction. And that puts a huge momentary load on the axle and all the bearings in the system and can damage the axle over time. And we've seen hundreds of broken axles from some hub companies which actually rely on single pull engagement to get high points of engagement. And it turns out it doesn't really work very well because it tends to break the axle over time, fatigues it, and is very damaging to bearing life. Now, ironically, you get single pull engagement quite a lot under light pedaling loads because there's not enough flex in the system for actually it to take up and start biting down on the other pulls. That constant shunting back and forth is going to fatigue the axle, it's going to wear the axle, and that's how axles ended up getting broken. Now, if you can't visualize what this single pull engagement thing is, where the free hub kind of jumps down very quickly if it only engages on one tooth, an analogy might be, let's say you've got your diff in your car where your prop shaft comes from the front, goes to the back, and the diff has like spreaders which bolt onto the chassis. If you were to take out one of them bolts where it bolts onto the chassis and floor it, the diff will try and rip itself round. And that's kind of... It's not exactly the same. It's like if you don't balance out the reaction loads, then the thing will move. That's kind of how I can put it. KOM haven't tried to get around this. They've tried to just cope with the problem because you can't physically manufacture pulls, ratchet rings, bearings, shaft to have like no clearance and no tolerance stack up. So you will tend to get single pull engagement on every type of hub. It's not a problem on DT Swiss star ratchet type hubs because their engagement is kind of axial, coaxial, not radial. But anything with an outward flinging hub, you're going to get it. Now, this is mitigated in this hub by basically doubling the size of the ratchet ring and the pulls. So the pulls in this are massive compared to normal pulls. And I'll drop in a picture here. If you double the diameter of the ratchet ring, you're halving the loads on each pull. The influence of e-bikes coming in. So the e-bike has got, so much more torque than a human can put out. And it's not just about the ultimate torque. Well, it probably doesn't have more torque than a human can put out in terms of absolute terms, but it's the repeated high torque fatigue that e-bikes can give an axle that's really damaging. So this, I think, should be adopted for all e-bikes. Now, having said that, even star ratchet systems can be broken by e-bikes, and it's not the pulls that tend to get broken, it's the actual spline where the two ratchet rings are sliding axially on. That can get stripped by e-bikes, and I'll drop in a picture here. Now, the other cool thing about this is, like I said, the disc brakes are part of the ratchet system. So you can unbolt these 4 screws, which are the disc brake mounting screws, and take out this ratchet ring, put in another one. The ratchet ring is that part in black there. You can drop in another one, different points of engagement. You can have high engagement, low engagement if you like it quieter. And it's very easy to change the disc. There's nothing, well, it is proprietary, but you don't have to modify the frame, the caliper. They make all types of disc sizes. And now the discs they also supply, KOM, are super high end. I would say the material hardness is probably a little bit harder than what I've seen on other disc brakes. And as you know, I make my own disc brakes and I've hardness tested these and they're up there. Having a disc brake that's too hard is not always good because it takes ages to bed in, and sometimes it won't bed in. These take a little bit longer to bed in, but once they're bedded in, they are very, very good, and they will last for ages the harder they are, but they do take a little bit longer to bed in my experience. But they are perfectly lapped, the flatness is amazing, the surface finish is amazing, and they make all different sizes. Overall, what's the ride experience? Well, I must just stress, again, that there are no modifications to the bike required to run the system. There are other things happening in the mountain bike industry at the moment where they're trying to basically completely redesign the rear mech system, hide the rear mech in the rear triangle, or they're going to gearboxes, and it's all looking a bit like uncertain what the future is. But whatever the future is, this will work with all of them. Now, the only thing I would say about this is when I first rode it on my Mega Tower, I put the bike, and I've got a wheel set. I've got a DT wheel set with the same rim and the same spokes with a DT hub. So I can directly compare the stiffness for both wheels. And when I put this in, I grab it at the top of the wheel and hold the rear triangle and try and flex the wheel. This is a lot stiffer. So it's obviously the center of all that flex when you're doing that kind of basic wheel stiffness test is the hub. So the axle layout and the bearing layout makes it a lot stiffer. Now, a lot of downhillers or enduro riders are trying to make wheels on some courses less stiff, so they track a little bit better from side loads. And whether this is too stiff, if you've got a very stiff bike frame, like my Mega Tower, the tube size of the down tube is super, super chunky. Out of plane, it's a very, very stiff bike because obviously it's a Santa Cruz and they add wall thickness as well because they've got a lifetime warranty. It's not the most forgiving bike to ride. And at some points I'm thinking maybe this is too stiff, but again, that's completely subjective, I'm not sure. Certain downhillers are changing their wheel stiffness for certain tracks, and they do that by changing the rim and the number of spokes. So there could be a scenario where this is too stiff. What that is, I'm not completely sure. But I do think for big hitting e-bikes where you want to fit and forget hub, this should be adopted instantly. Now the weight, you might think having an axle within an axle and a free hub which goes the entire length of the hub is going to add a lot of weight. But it doesn't, because what you end up doing is thinning down all the walls of the outer hub shell, so that saves quite a lot of weight. It's similar to a DT350. It's slightly more than a DT240, but quite a lot less than an Industry 9, which is about 300 grams. And I think these start from 260. And off the top of my head, a DT240 and a 142 6-bolt is about 202 grams. So it's a slight weight penalty over a DT240, about the same as a DT350. So I think that's pretty damn good considering the extra reliability and longevity that you should be getting from this system. Rear hub design, I hope I've tried to convey this in an understandable manner, and the problem with doing something as clever as this is trying to explain how the benefits of this system work. Now a lot of people, particularly lightweight road riders, are going to say, look, I've never had a problem with longevity of a road hub. But you get e-bikers out there and mountain bikers out there, or even road riders that are heavier, who tend to destroy ratchet rings, destroy bearings in hubs quite frequently, particularly if you're not that keen on cleaning your bike and you ride it in muck all year round. And these are made in the Peak District where it's mucky all year round. So that is, I think, the market for these. But there's no reason why. I mean, they do offer these in the road market, and the weight can be 260 grams, so you can still make a pretty good wheel set out of this for the road. And what those efficiency results, so the roadies, I think, are going to be interested in that extra efficiency from not having that axle bending. That needs its own test rig that you can apply a static kind of radial load or even a dynamic radial load while spinning this at set power. Thanks for staying around. This has been a really long video. I hope I can shorten it down by the time I edited it. Get in touch with me or KOM to learn more. If you want some more info from me, some more kind of subjective feedback from me, get in touch with me. This was obviously gone up on my Patreon way before I've revealed it to you, so all those guys know about it. But if you do get in touch with KOM, don't forget to tell them that Peak Talk sent you, and they'll take it from there, and you can build this into a wheel set yourself, or you can buy a wheel set from them. But I think this is a game changer. Cheers, and I'll see you in the next one.